All right, we're going to be hearing today from two of our extremely productive CLEAR trainees. They're going to be jointly presenting on the topic multidisciplinary approach to screening neighborhoods for below ground volatile organic compound contamination. Again, we have two biological sciences and urban sustainability. She's a previous NSF fellow through the T-Rust program, which is funded through the National Science Foundation. She is currently a leadership fellow for CLEAR. She has her master's degree in plant biology from Southern Illinois University, a bachelor's degree in biology and Spanish from Valparaiso University in Indiana. Our second speaker today is Qisen Wang. He is a doctoral student in the Department of Civil and Environmental Engineering. He's a CLEAR trainee for Project 2. He has a master's degree in computer science from Syracuse University. And currently, Qisen is focused on real-time monitoring and predictive analysis of soil vapor intrusion. Just like all of you, I'm very excited to hear this presentation by our CLEAR trainees and fellows.
For that lovely introduction, Carol. It's about disciplinary approach.
The mic is cutting out.
Okay.
Oh, okay.
Is someone able to put into the chat we're having technical difficulties? Does this work? Okay. Ethan, I think we're about to get up close and personal together with this mic. All right. Okay. All right, sorry about that, everyone. Like I said, my name is Sarah Black. I'm a dual title doctoral student here at Wayne State in both biological sciences and urban sustainability. My dissertation is advised by Dr. Glenn Hood of Project One of CLEAR, and I study how do contaminants move through the urban environment as they are mediated by plants. Today, specifically, I'll be talking about an aspect of that, which is phytoscreening. As Carol mentioned, I am a CLEAR trainee. My background is in botany. I did environmental regulation for a little while, and before that, I kind of wandered my way through undergrad trying to figure out what I was going to do, getting Spanish, biology, and humanities all thrown in together.
Hi, everyone. My name is Qisen, and I'm a PhD student in the civil and environmental engineering. Right now, also a trainee in the CLEAR project E2, and I got my master's degree in the Syracuse University. And I don't want to mention that why I changed from the computer science to the environmental engineering. That's a long story. And right now, I'm working on the real-time monitoring and trying to predict the soil vapors of the vapor intrusions. So I was started to introduce why we want to do this project, because the Detroit area right now has the highest preterm birth rate among 100 cities in the U.S. With the greatest birth numbers. And so the CLEAR working groups thinking that the environmental exposure to the VOC, such as benzene, toluene, xylene, BTEX, and the TCE, PCE are the most important reasons why we have the highest preterm birth rate. And so under our project, we have 5 sub-projects, which is file studies and also the sensoring studies, and the rest 3 are the testing for the human body's reaction influence on the VOCs. And today we are focusing on the first 2, E1 and E2, which is a field study and the sensoring and remediation part. So for the audience who are not that familiar with the VOCs, which is volatile organic compounds, which come from the human's activities. The definition for the VOCs is that any compounds of carbon which participate in the atmospheric photochemical reactions, and it will evaporate under normal indoors conditions of the temperatures and the pressures. And also it will just lasting for a long time in the waters and airs, and typically used as a solvent in the industrial. And so our goal is to reduce the concentration of the VOC as low as possible. So here is a map of the brownfield and in the Detroit area. In this map, you could see the green spot, which is the brownfield location with the potential VOC contaminations. So the brownfield is the abandoned area which was used as a commercial or industrial area. And so usually there is the containers, the gas containers or the pollutant containers on the ground. So after many years of the leaking from these containers, so that location will be the brownfield and will influence our health. So you may wondering why we will influenced by the VOCs, you mean? So the VOCs will just flow with the underground waters, and it will just under your house or near your house, and also the vegetables we eat in the life. And because of the gas diffusions, the VOCs will just goes into your house, and you will get in touch with it, and also the plants or the vegetables we eat. Next, I'm gonna turn over to Sarah for the next.
Yeah, thanks, Qisen. So one of our major struggles, if you could go back a slide. So one of our major struggles is that we have these plumes of contamination that are moving underneath the city after they leak out of this leaky underground storage tank. But from above ground, that's very difficult to know where they are and how they're moving. Previous research has told us they could move as far as 1 kilometer, about half a mile from maybe where they initially came out of, depending on their concentration in the movement of water. So this pushes us to come up with alternative ways to find out what's the below the ground. How can we delineate out so then we can later on remediate? Next slide. So the traditional way to do this, and you can see the blue columns in my pictograph here, is to do drills, to do groundwater monitoring or to take soil samples. And that works pretty well. And actually it's well established and it's used in the literature, court cases, remediation, et cetera. But it becomes problematic when you're in an urban area that has a lot of private property. Getting those kinds of rights and access can be difficult. As an alternative, phytoscreening has been developed. Phytoscreening is the use of plants, typically trees, to detect below ground contaminants. The roots, as you can see in my pictograph, touch the soil and the groundwater, and they then will bring up water and everything else that's in it. This is fairly well established for metals, but in the last 10 to 20 years, there's been a growing reach to find out if we can use them for organic contaminants, like volatile organic compounds. There has been a struggle for VOCs. There has been some research, especially out of Missouri S&T, suggesting that you can use trees, but it is in such small amounts that the technology really hasn't come until the past 10 years to detect VOCs. Next slide. These are some pictures of brownfields here in Detroit. You can see sometimes the slabs are left or it's just become a grassy area. But notice there's a lack of tree canopy. In places where phytoscreening has been used before, we're usually talking about large wetlands or forested areas or in our rural communities where there can be a lot of canopy. But here in Detroit, there's not. And that causes multiple problems for phytoscreening. First, when you take tree cores, meaning a segment of a tree trunk, that is injurious to the tree. And if it's already in a polluted site, if you took multiple cores throughout the season or even across years, you kill the tree. I would be incredibly unpopular if I walked through many people's neighborhoods and homes and immediately killed their trees trying to determine if their groundwater was contaminated. And so we have to think about alternatives for phytoscreening. And for us in our neighborhood, as I show in my pictures, you have to look below your knees. Look at shrubs, look at our herbaceous tissue, because everything that's growing, as you can see in these pictures, are what I would call less beloved plant species, also known as weeds. And so the project I'm part of is starting to think about, can you use herbaceous tissue, non-woody tissue, to detect and use as phytoscreening tools? This brings me to Project One of CLEAR. Project One of CLEAR's goal is to use above ground plant tissue to detect, delineate, and find VOCs, and eventually create a predictive framework that if we test plant tissue above the ground, we can eventually say, yes, possibly in this neighborhood, yes, in your home, there might be a risk, or no, there isn't a risk. And we can do that through simply tracing what's in the groundwater and possibly even use isotopes if there are multiple contamination sources to be kind of pollution detectives and find out what's happening. All right. I do not work in a vacuum. Project One is full of many people, particularly the principal investigator, my advisor, Dr. Hood. We have two postdocs, Dr. O'Leary and Dr. Palilil, and also graduate students such as Bailey, who works closely and is in the chemical analysis core, and our lab manager, Grace Sweck. So the first quest for phytoscreening, and to make sure it's applicable and we can use it in the urban environment, is to find the perfect plant. This was our summer of 2023. You need three things to have a great phytoscreening plant. It's got to be tolerant for a range of places, from clean to extremely dirty. It's got to be able to survive all the salt we just put outside for all the snow. It's got to survive in sidewalks. It's got to survive in slabs. And it has to compete with clean areas where there might be a lot nicer plants or healthier plants around. That's the first problem. And the second problem, it has to be ubiquitous. If I walk onto any brownfield or any back alley or any remediated site, will I find these plants? And after many, many long hours in a car and lots of time walking through many sites throughout the city, Project One came up with 5 plants that we thought were very possible. The first one on the top left is Tree of Heaven. That's an invasive tree here to the United States. It's incredibly aggressive and usually appears as a shrub. unless it's being cultivated. The second is Siberian elm. It is also a tree, but usually you find it as a shrub. When Dutch elms disease killed American elm in Detroit, this was brought in as replacements, and it has spread quickly throughout the city. On the bottom are our forbs, our herbaceous level, kind of what I was talking about in our hopes that are usable in the city. The one on the far left is goldenrod, that is a native to Eastern North America. The middle is red clover, which is a naturalized, very common in lawns, very common in sidewalks. And last is grapevine. Grapevine straddles between being a woody and herbaceous plant, depending on how old it is. And it grows on any crumbling infrastructure here in the city, any fence line. And so these seemed like the great candidates to choose to find out, can you detect VOCs using them? And so that leads to point 3, where we spend collecting them to figure out, is this the right plant? Next slide. So in 2023 and going into 2024, we went to spots that we knew were highly contaminated. Qisen will talk more about this site later, but this is Conant. It used to be a dry cleaning where chemicals were improperly stored into the ground. And so it has quite a high amount of the BTEX compounds, as well as TC and PC. You can see we're standing on the slab that was left after remediation. There are many chemicals still underneath the slab. And you can see in my picture all of my named plants. On the top left, there's Tree of Heaven growing. Right behind Grace, there is Siberian elm. There's goldenrod growing, and then there's grapevine. And then in the far right picture where you see Brendan taking a soil sample, there's red clover in the background. So they're there. They're existing on our contaminated sites. What we do is then we didn't take plant samples. I have a grapevine in my hand. I pulled out a large section of grapevine that had a root, a stem. It also had leaves, and grapevine not so much, but also if they had flowers. We were testing every plant tissue we could find to see if the plant is holding VOCs. We then cut it up into its different plant organs: leaf, shoot, stem, root. And then we placed them in these small little vials so that we would be able to test them for VOC. We put in 10 milliliters of water and an amount of plants. The water traps the VOC until it can be tested. And as Grace is holding and I'm holding in the middle, we are packing them full of tissue to be tested later in the lab, where they're put on ice until they can be run at the chemical analysis core. So we collaborate, this is a core of CLEAR, to use solid phase microextraction, often called SPME, where they use a fiber to collect the VOCs when the plants are heated, and then run through this machine where they can detect BTEX, TC, PC, and I'm sure very many other chemicals to the parts per trillion. We know health risks start in the low parts per billion, perhaps even as low as 10 parts per billion. And so this helps us understand and connect those things together. So to the plot. We have our 4 plants where we looked at, can you hold these volatile organic compounds? Red is goldenrod, green is red clover, blue is our Siberian elm, and purple is our Tree of Heaven. And next slide. And when you look, we see right away that root has the highest amount of VOCs. This is not a surprise. Root is closely in touch with soil and the groundwater, and so it makes sense that it would have the highest amount of VOCs over everything else. However, we can see in smaller amounts, flowers, leaves, and shoots, stems, for goldenrod are also holding significant amounts of VOCs. But VOCs in general, some of them are more concerning, and we want to know the breakdown. Are some plants better than others if we're looking for a specific chemical? This is for all of the BTEX. Along the x-axis are all the different kinds of plant organs, and along the y-axis is our different BTEX compounds. And when we look, we can look at benzene, which is on the top left. We see that in general, red clover is holding in its roots, in its flowers, and its leaves and stems, higher amounts of benzene when they're all harvested from the same site. Going across to toluene, we see that it's primarily goldenrod in the roots, but also in the flowers. Ethylbenzene, Similar story, except really it's only goldenrod that is finding it in the roots. And then in xylene, again, goldenrod, a little bit of red clover is finding it in the flowers, roots, and shoots. So this seems very promising. Next slide. And then we look at our chlorinated compounds, TCE and PCE. They are primarily in the roots and in the shoots, which suggests that chlorinated compounds, because being much larger and much heavier than our BTEX compounds, they can't really leave the vascular system, the circulatory system of the plant, suggesting if we're looking for these in particular, we need to focus in on looking at their stems and their roots, particularly stems as above ground tissue. And then again, our goldenrod and maybe red clover are coming out as the winners as we start to phytoscreen the city. But we have other concerns. So we know if we collect them right away, there's high amounts of VOCs. But last summer in 2024, we collected 10,000 samples between June and September. It was a significant amount of samples. And the chemical analysis core can run maybe 200 to 300 a week. So we have to know if we can store VOCs long-term in cold storage, -80 centigrade. So we had an experiment where we tested samples 1 day after they were collected, 2 days, 2 weeks, a month, 3 months, and 6 months. And when we look at that, there's a significant, except for Siberian elm, negative correlation that happens over time, that they are losing VOCs even when we keep them in cold storage. But goldenrod appears to continue to be our winner because even though it loses a significant amount of VOCs over time, it is still in such high concentrations that we'll still be able to detect something in goldenrod. When we break out from all VOCs and we look at tissues, we see that roots lose the most amount, but they had the most to lose. But some of our other tissues in goldenrod, the pink is flowers, the green is leaves, may be better in the long term if we're looking for storage, even though they decline continuously over time. And we found that benzene must be our most sensitive to loss. And so we'll have to take that into account if we are looking for benzene in our future collections. Now I'll turn it over to Qisen.
Thank you, Sarah. So I'm gonna first introduce our group as a Project E2. We have so many graduate students here, and also we were leading by Dr. Weger and Dr. Dietrich and Dr. Miller, who is here supporting us. Thanks, Dr. Miller. And so first, Project E2 is trying to We are trying to find a way to addressing the challenges of the vapor intrusions and the remediations. So we have 3 parts. In one word, the first part is that we want to find it, which is sensoring. And the second part is that we want to predict it and in the future. And the third part is that we want to get rid of it, the remediation part. So today I'm going to focusing on the first 2 parts, which is the real-time vapor intrusion monitoring and prediction models and applications. Next, please. So before the field work, we trying to figure out which kind of sensors we are trying to use. So we need the sensors to be high sensitivity so we can find out the lower concentrations of the low concentrations of the soil vapors. And also we need these sensors to keep working for a long time. And the third part is that we need it to be easy to be deployed in the field. So after the researching of the sensors, we find that the PID sensors is working best for our goals. So we are doing some lab works, the sensor calibrations. We are trying to see how the PID sensors works. And then we're using the standard gas is isobutanene to test it. We see that the sensor reading is a highly linear relationships with the concentrations going on. So after that, we keep doing our field works. So the first part, we are trying to build our monitoring systems. You could see in the pictures at the middle of the slides, It has a big box at the bottom, at the top, and connected with PVB tubes. In this box, we have the batteries, the PCB board, and our data loggers inside. So you could adjust the PVC tubes as long as you want to see all the depths you want monitoring. And at the bottom of the tubes, we placed our PID sensors and the temperature and humidity sensors inside. And we also replaced some plugs around the bottom of the tubes, which can prevent the water outside and letting the gas going inside. But you could see these plugs as working as active carbons, but it will not absorb the gas. It will just letting the gas go inside. And we also placed the passive samplers near to our sensors, which will work as calibrations there. We will replace the passive samplers every week and send it to the lab using the GCMS to see what exact the chemicals there. Because the commercial sensors, PID sensors we use right now from the market can only give you the total VOCs concentration. It will not allowing you to know what exactly the chemicals it is. And for the data part, we have two ways to keep our data. So the first part is that the data loggers we placed in the box, it will just store our data every 30 minutes. And if our system is under the Wi-Fi conditions, it will just send the data back through the Raspberry Pi to our database. And we could go through all the data from our web page. And you could see the data format here at the right of the slides. So in the summer, me and Brandon and other group members are doing some field work in the Collins Street, which we mentioned before. At this part, we have two locations to place our tubes. And each site, we have two tubes there. One is 1 feet deep, and another is 3 feet. Another is 3 feet. So also you can see the metal tubes are near to our PVC tubes, which we placed passive samplers there. Next. So here is some raw data from the Collins Street. You could see that the dark blue line here is the concentration of the total VOCs, and also the yellow line is the temperatures. The green line is the humidity. It is obviously that the temperature is has a positive relationship with the concentrations, but the temperatures may not. And also we're adding the rainfall data into these graphs. So we want to see how it will influence our concentrations. But it is not that relative to the concentrations. So after that, we compare the passive samplers reading with our sensors to see how the trend it is to make sure that our sensor is working well. So the most of the time we see that the trend of the sensors is going down and up with the passive samplers, but sometimes maybe the concentration is going fast, so it won't. So after that, we are trying to predict the trying to build a model which can predict the data by the ambient air's temperatures, humidity, and the air pressures. So the four models we choose is the partial least squares regression, artificial neural network, and support vector regression, and random forest regressions, which are the four popular models we are using for the predictions. And how we are evaluate those models is we using the R-square and the mean relative errors and the standard deviations. So you could see through this plot, the blue one is the random forest regressions, which has the highest R-squares, and also the mean relative error is low, and also the standard deviation looks good. And also the ANN, artificial neural networks, is also working well. But all the others is not that good. But there are also some problems we are trying to testing the modes. The mode will works good on our testing data. When we are training that, we split the data into 80% to train them and rest 20% to test it. It will work good. But when we are using another location of the census reading to test it, it is not that good. Maybe that is because the condition of the underground water may change immediately in 1 or 2 days. So when we are train the data to use the ambient air, because ambient air situation is stable, but the underground is not. It may not. So it will just have a big peak in some days, and the predict results is not that good. We are trying to figure out how to change it. Maybe we were adding more parameters in the modelings. And the second part of our project E2 is that we are trying to train the mode through the EPA's vapor intrusions database, which is paired with the prediction from the Johnson-Edinger modes as a training data. So this database contains the site characteristics and measured contaminants concentrations with 1,000 PCE and TCE observations from more than 500 buildings. And here is some background knowledge from, on the Bayes network we are using for the training. The Bayes network mode is a graphical probabilistics mode which provides the information about the variables. So you could see every edge and nodes is our data, and we will try to predict it. And so when we are training that, the data we choose is required from the JEM modes, and also we including other data such as the building used groundwater temperature and dips to the source and soil characteristics. So the results showing that the Bayes network works better than other traditional modes we used, and also the sensitivities of the mode varies a lot. The left part is that TCE, and you could see that it is more sensitive to the building used, and also the red part is the PCE. It is different from the left part, but the accuracy of the this mode is better than the traditional ones. So for the future works of our networks, Bayes networks modeling, we are trying to improve the accuracies by testing the various different data. And we are trying to compare the Bayes networks with other modes. And also we want to validate these models with training by our fieldwork data from the corner street or other homes visits. So I'm going to turn it to the Sarah.
So how do Project 1 and Project 2 come together? These field studies, how do they reach the goals of CLEAR? And it is really through our joint project with the Community Engagement Corps, the goal of screening homes. What we do at each home is there's a collection of soil, there's a collection of plants, and then there's a collection of indoor air. And we come together, and the ultimate goal is to say, can we predict from the outside, without having to invade someone's home, the quality of their air? And I'm going to talk about a few homes that Project 1 collected in June, but I'd like to note that Project 2 collects all year round, including in the freezing cold, along with the Community Engagement Corps. Next slide. Community Engagement Corps is directed by Lake Thompson from Urban Affairs, and I have to give them a lot of credit because they do all the outreach. They coordinate all the visits, they call, they recruit. They're the ones that ultimately handle compensating our neighborhoods for this kind of research that we do. And they also reach back if they find concerning levels of VOCs to talk to the neighborhoods about how they can reduce their risk. Their goal through the life of the grant is 500 homes, and I think they're maybe a quarter of the way through that at this moment. So this is from June and early July of 2024 for Project 1. We collected about 10 homes, and we collected I would have liked to use goldenrod at every home, but of course you cannot go back in time and tell them to plant goldenrod for us to test. And so we kind of used whichever plants we could find, generally tending towards the weedy plants that we wouldn't destroy their lovely landscaping or other things. And we found some concerning things, particularly at 3 homes. We found to have plant tissue harboring total VOCs above 1,000 parts per billion, which, as a reminder, health risk tends to start around 10 parts per billion, perhaps less with further research. That was most commonly driven by xylene, and it would be very high in plants, even if it wasn't highly available present in soil, suggesting that plants are either also getting it from the air or they're more than just a snapshot in time. Soil, groundwater, it's a snapshot in time, but perhaps plants are accumulating xylene over weeks. And so it may be more indicative of what kind of exposure people are having in their homes over long periods of time. We didn't find a linear correlation between soil and stems and leaves, but that's not unexpected. Previous literature has suggested that there is more of a cubic or quadratic kind of relationships going on. And so when we look house by house, houses on the x-axis and VOCs and their concentrations are on the y-axis, we continuously see that soil may have very low levels of VOCs relative to the plants. And we looked at flowers, leaves, roots, and stems, flowers being in red, stems are in purple, leaf and roots are in those greenish kind of colors, suggesting that we are seeing some kind of larger snapshot, or perhaps we are seeing an accumulation, which again goes back to how far back can we predict exposure. And then when we look particularly at benzene, which is something Project 2 is also very interested in, we see that we find benzene in plants at much higher rates most of the time at most houses than what's in the soil. And when we compare Project 1 and 2 together, Project 2 admittedly has a lot more homes already analyzed. We see that the benzene concentrations, homes are on the x-axis, benzene concentrations are on the y-axis. We see that in general, plants are having it in higher concentrations than what is found in the soil. And so they're looking forward for us in future directions. Next slide. We have to figure out, is there some kind of correlation? Is there some kind of correlation? And then when we combine this with the community engagement course data, can we get into predictive power? If that 1,000 parts per billion of xylene that we found at those 3 homes, is that predictive of how many VOCs are found in the house for either from ground contamination or some other kind of risk inside the home? That integration of data will ultimately further clears goals. Science is never done in a vacuum, and I cannot appreciate more the Community Engagement Core, the Chemical Analysis Core. I'm currently funded through the Research Experience and Training Coordination Core. I'm also funded by Cures, and I talked a lot about the people who are directly involved with Project 1, but of course, the Hood Lab is much larger than that. There was a small army of undergraduates who helped us. There have been other graduate students, and I'm deeply appreciative to all of them and their work. And that's it.
Yeah.
We'll take any questions. Thank you. So Carol Miller just complimented me on my pictograph of the leaky underground storage tank leaking into someone's basement. I made that for the 3-minute thesis competition last spring. Thank you. Yes. Hmm. Yes. So the comment was about doing linear regression and considering non-parametric regressions for our time series data, the data that was 1 day through 6 months, if I understand your comment correctly. Yes, I made a Spearman-Ranks correlation very quickly for this. But yes, we do need to consider interactions, and we will before we go to publication later this year. Yes. The botany questions that keep me up at night. Yes. Okay. So the question is there a concern because tree roots reach much deeper into the subsurface than herbaceous plants? Yes, there is a concern. Fortunately, Detroit helps us by having a rather shallow water table that isn't obviously replicable in other places. One of the reasons I didn't talk about that I favor goldenrod, one of our native plants, sometimes known as a prairie plant, is that its roots go down about 4 feet sometimes, and it can be quite in depth. That is similar to some small trees. And I guess although we look at groundwater a lot, we're really looking more at the interstitial water that's getting pushed up underneath the slab. And so I expect that chemicals will be very close to the surface because slabs in general are really not that deep. Yes.
Okay, I have a question from the chat. Marcus Friedrich, I think we covered some of this already, but he says, what is the root depth of goldenrod? Is there a way to estimate the soil VOC levels from the root concentrations? If not, would it be worthwhile to generate a reference panel data set? The benzene data indicate a more complicated story.
Yes, to all those questions. I struggle with the use of roots, although I acknowledge that they have the higher concentrations of VOCs because we're really looking for above ground tissue. Our whole goal is, can you estimate VOCs from the surface? I think eventually one of our goals, in the hopes that phytoscreening will be used like groundwater monitoring that are accepted in court cases, that are accepted for remediation, we have to come up with those kinds of tables. And when I say we, I don't mean just Project One. I mean like the phytoscreening community in general, that there has to be established kinds of ideas of this much is in plant tissue, it's a problem and it needs to be remediated. But whether that we'll have that within the next 2 years or like the life cycle of Clear Grant, I'm unsure. Yes. I don't know how we, so the question is, how do we select our sites, both for Project One and Project Two? I'm unsure how the houses are selected. The Community Engagement Corps handles that for a lot of privacy reasons when it comes to health. I can tell you that they try to target different neighborhoods. There's a particular neighborhood south of the city airport that has been dealing with specific contamination issues, and they did an extreme significant amount of outreach to that neighborhood. However, how does Project One? So I combined quite a few of our like goals in Project One for brevity, but one project we did, I called roadsides, where we just chose vacant lots every kilometer and tested it. Abandoned lots, I call them kind of the forgotten places. Detroit is 20% vacant and abandoned, and so it's not that difficult to find an empty lot where something used to be. Eagle did help us. They have a report, a list of what they call lust sites, sites that had leaky underground storage tanks, some remediated, some not. So we did target some sites like that. But some of it to populate the grid or to like flesh out all of Detroit itself, we used major roads that we knew have had a lot of commercial effort on them, such as Woodward, Fort Street, Jefferson, both current and historical, and we just started sweeping through the grid. And Qisen can tell you about Project 2.
Yeah, Project 2's goal is trying to grab as much as possible the houses in the Detroit area, and finally we can draw a map of the concentration of the underground soil vapors. And so through these maps, we could find that the hotspot of the Detroit areas, which has a higher concentration of the VOCs. So finally, we can do the remediation of that and get rid of it.
I stray away from this. So the question is, have we tried to use public schools or police stations that are evenly distributed throughout the city? I do like that idea. I would stay away from schools just because of the sensitivity of minors and concerns there. Police stations, I would think about. I would actually think post offices, if we were going to go that route, would be great. We do kind of, this goes back to the roadside project of how we tried to represent by using major roads. We can talk more offline about that, but Detroit is built like a wheel because it was built in the French style like 300 years ago. And so it's easier to choose all of the roads that radiate out of Campus Martius and just sample in a very systematic way. Yes, on the far end.
So when we are doing the question is that is there any influence on the soil textures, right? Yeah, when we are trying to putting our passive samplers at the house, we also grab the top soils at the depths of where place the samplers. So when we will analyze the soil textures and all the humidity parameters and something like that, but right now we haven't done and we haven't finished the analysis part, but it must have some influence on the soil vapor concentrations of that, because the soil temperature will influence the is that easy to evaporate from the groundwater through outside on the ground. I think we showed a great example.
I think that's a better question. Oh, so the question is higher integration between clear projects and cores. Your specific question, Mike, I think is actually a better question for Dr. O'Leary. But I'm here on the stand. So yes, Dr. O'Leary, Brendan, won the Casey Donnelly Fellowship last year to kind of understand how soil, sewer vapor, soil vapor, and plants may all connect together. And I think that is one of the strongest ways that Project 1 and 2 will come together. And then as for are projects that work more on the human health side of things, I'm not quite sure how we'll connect more directly, but always willing to consider more ways.
Yeah, I think for the model training things that, so right now we are just using the ambient air pressures, temperatures, and humidities in the predicted models. But so that's why when we are putting our models to test it in a new data set, it didn't work well, it didn't perform well. So the more parameters we put into the model, I think the model will more robust and it will be strong to immediately changed to the concentrations and the data. That's why I think